Hello. Today I'm going to talk about open source JuMP package called hydropower models. It is a joint project from FGV Energia and in the Laboratory of Applied Mathematics, Programming and Statistics from PUC-Rio. The objective was to create a flexible enough tool to help the energy sector to test new ideas using state-of-the-art technology in problem formulations for network optimization and hydrothermal dispatch, and using the state-of-the-art offshore technology for solution, STD. Well, this introduction, I'll give a quick introduction about who I am in the package, the dependencies, and if we have time, a quick example. So I graduated from control engineering and double degree in PUC-Rio and double degree in general engineering in Centrale Marseille, École Centrale Marseille in France. And I'm currently enrolled in the Masters of Operational Research, and I work at the Laboratory of Applied Mathematics, Programming and Statistics. Well, hydropower models is a JuMP package for hydrothermal multi-state steady-state power network optimization solved by stochastic dual dynamic programming. The problem specifications and network formulations are dealt by our models, while the solution method is handled by SDP.jl. Our models package was Coffin published a paper in 2018, and Oscar Dawson published a paper with Kapelevich in 2017 about his package, SDP.jl. Well, this is a workflow of the hydropower models. Power models, as I said, handles the problem specification from input files and creates a network optimization problem, which I then pass. I make some modifications, making it a hydrothermal dispatch optimization model from input files given by the user, and this model then I pass to SDP to solve the problem. Well, this is only possible because of JuMP, who comes for the rescue, and yeah. Well, Power Models is a steady-state network optimization framework. It provides utilities for parsing files, so you can have an archive of optimization, network optimization problems and solve it very easily. It was designed to enable different completion evaluation of different problem formulations and algorithms. And the code decouples problem formulations and problem specifications. Well, so you can have an optimal power flow of a DC approximation or a relaxation of circularization, SDP relaxation. So there's a workflow from an input file. We choose problem specification and a network formulation. And from this, we can have a network optimization problem, which it gives us a JuMP model of that network optimization. We then, as I said, make some modifications from input files given by the user, which I will explain a little bit later. But in general, it defines the water management and the inflows from water and scenarios probability. And then I create the respective variables and constraints. SDP.jl is a JuMP package for solving large multi-stage convex optimization problems using stochastic dual dynamic programming, which was introduced in the seminal paper of Mário Pereira in 1991. Pereira and Pinto. It's an open source package, and it's generic. Well, there are other packages for solving SDP. Why we use the one from Oscar Dawson? It's easy to use, easy to extend, and has many features. So it was easy for us to get used to it and start using it. And SDP, once we get the hydrothermal dispatch optimization problem, we pass it to SDP, which uses it to define one of the sub-problems from our multi-stage problem. Well, so the only difference from the problem we had before, that we have now a future cost function which is the relationship from one subproblem with the next stages. In this case, the expected value of the objective value of the future stages, which then simply said SDP tries to approximate using a piecewise linear function, outer function. And then with this function, we are able to simulate different scenarios from the problem we have specified. So if we have time, I believe we do, I'm going to just show a quick example. So our example has two thermal generators and one hydroelectric generator. Everyone with its expected maximum generation, and an expensive generator and a not so expensive generator. We're going to solve a DC approximation from the optimum power flow problem, which has the Kirchhoff's laws, which are the energy balance, the hydro balance, which is the management from the reservoir, and the relationship between the water turbinated and the energy generated. In this case, the production factor is 1, so every cubic meter generates 1 megawatt hour, and the respective bounds. I forgot to show each. So how do you use this package? Once you have defined the problem, so the maximum of your reservoir, how much you can dispatch, for example, and the inflow scenarios, how much it rains, and the probabilities of those scenarios, and you have passed to power models. You have one case of grid for power models. You can use the package. So import the package and the solver you want to use, and you pass to this function the folder where you have all those input files, and it will generate a dictionary containing all the information from the problem. So you can then choose which problem you want to. You have now a problem specification defined, and you can choose how many stages you want, which approximation you use, or relaxation. If you want to run optimum power flow or power flow, for example, and the solver, which this function creates a dictionary, which will be passed together with the data, so you can generate the multi-stage model. Then you are able to run the SDDP with this function, and once our model is trained, we're able to run different scenarios for a multi-stage optimization model, which then returns a detailed dictionary containing all the information from our simulations here and some extra information. This would be the information from the 10th simulation, for example. That's how we would access it. And plotting results is easy. So the plot results function plots the common plots you want to see in a hydrothermal dispatch optimization problem. And that's it. If you want more information, it's on the docs of our package. Under examples, we have scientific reports with some special cases, if you want Jupyter-like cases. And this is part of a bigger project from our laboratory, which is trying to generate, put all its development, academic developments in open source projects. So you can also access the GitHub from LUMPS and see the other projects. Thank you very much. Yes.
We're solving non-convex problems using a convex framework.
Non-convex? Yeah. Where you are able to solve non-convex problems, as for example an AC optimum power flow, which will be then just be I'm convexifying this problem and finding a local maximum and heuristics to this problem. Yes.
So you get the sum of an SDDP project, and you just end it up down models and populate. Is that right?
No, sorry. Can you repeat the question?
How does models populate that piece?
It gives us the JuMP model, and I'm the one making the link passing to STDP this JuMP model. Okay. Any more questions? Yes. Well, we have found that using the problem specifications we have already, we are able to run more complex problems than people had already and see that the true cost of operating a system will be higher than what they expect. But we don't have a lot of results yet. It's just the framework for helping people generate those results and studying special cases.
Thank you.
Thank you very much.